Hello everyone, greetings of the day. This is Lakshmiramana, working as assistant professor in Computer Science and Technology Department, Madanpalli Institute of Technologies. Okay, Madanpalli Institute of Technology and Science. So in today's session, we'll be discussing about process synchronization. So here are the contents of the flow for process synchronization. We'll be discussing first, we'll define what do you mean by process synchronization. Then we'll see with some example, what is the need for process synchronization? Why do I need to synchronize the processes? Then we'll define what do you mean by critical section problem and the solution for the critical section problem. Then it is followed by the summary of the session. Okay. So now first we'll define what do you mean by process synchronization. So as we know that, so we are having two types of processes, namely independent process and the cooperating process. So the definition of independent process is that a process is independent if it cannot affect or be affected by other process executing in the system. For example, if there are usually in multi-program we will be having more than one process running at parallelly. So a process is called to be independent if it is not affected or it do not affect other process, then we can call that process as independent process. And coming to this cooperating process, a process is called cooperating if it can affect or get affected by other process, then it is called as cooperating process. So when do a process will get affected? Because when a process shares some data or some other resource with some other process, then definitely then that process can easily get affected or create effect on some other process. So in reality, we will be having most of the process will be of cooperating process. Now the question comes, now we'll define what do you mean by process synchronization. So when all these cooperating processes are running, so we need to ensure the orderly execution of this cooperating process. So the ensuring of orderly execution of cooperating process is called as with maintaining the data consistency. So here the term data consistency is more important. I need to maintain the data consistency, then that orderly execution which maintains that data consistency is called as process synchronization. Clear? Now, so after seeing this definition, now we'll move on to the next session. What is the need for process synchronization? So let's see the famous classical problem of synchronization problem. So the basic problem is your producer process and the consumer process. What is this producer consumer process? So in this process, we'll be having two types of processes, namely producer process and the consumer process. So here the slide will be showing the code for your producer process. So let me explain this briefly. What is this producer consumer problem? Let me have this one. So let me have this, this is my, so this producer consumer problem. So I'll be having two process, namely producer process and the second one is consumer process. So what is the problem is that both the producer and consumer process will be sharing a common data. So that is a common buffer. This is called as buffer. So in short, I'm representing this buffer with B. So in this buffer, this producer and consumer, they are sharing this buffer. Okay. So this buffer is of some size, a fixed size. So assume that this is BS, the size of this buffer, BS. Now, what is this producer consumer problem? So here the producer will be producing some items. So the producer will be producing some, I'm representing this item as I. So the producer keeps on producing this item. For example, it has produced some item I here. And what is this consumer process? The consumer process will consume this item. So the producer will be producing some data into the buffer and the consumer is consuming the data from the buffer. So this data I'm referring as items. So what is the condition is that, so the producer process will be keep on producing the items until this one. So when it will stop, when it reaches when the buffer is full, the producer process cannot produce any. Even though it produces, it cannot store that produced item into the buffer. So it has to wait. Similarly, the consumer, if the buffer is empty, the consumer cannot read any item from the empty buffer. So whenever at least some item is there, then only it will consume. Clear? So these two processes are called as cooperating process. Why? The definition says that when two processes are sharing some data, so then these are called as cooperating process. So it will affect the execution of this process is affected by P, and the execution of P is also affected by consumer process. Clear, right? So this is how these are cooperating. So now the question comes, if they are executed sequentially, if they are not executed parallelly, then there is no issue. So, but in multi-programming, we cannot ensure that both the programs will be running parallelly, that is concurrently. So when both the programs are running concurrently, then definitely if a proper care is not taken, it will result in some wrong results. So we'll explain that how the inconsistent data will come. So before going to that, let's see the code here. So this is a code for producer program. When it is true, it is a true condition. So always these statements are true. So while true, the producer, what does it is doing? It is producing some item, and that item is called as next produced. Clear? So then after producing this item next produced, what does it will do? It has to check the condition, because just now we have seen that a produce, if the buffer is full, the item with whatever the newly produced item, it cannot store because there is no space in the buffer. So I need to check that condition. So what is this condition? When counter is equals to buffer size, do nothing. So we are maintaining, so both the variables, so both these things. So I'm maintaining one common variable called as counter C. So here it is counter C. So what does this counter will see? That it will always gives the number of items that are present in the buffer. So C represents the number of items in the buffer. So when counter is equal to buffer size, what does it mean? That the number of items are equals to the size of the buffer. Means if the size of buffer is assumed that it is 10, the maximum size, if the counter is equals to 10, so it means that there are 10 items in the buffer. So that is the condition. When counter is equals to buffer size, what the producer has to do? It has to do nothing. It has to wait until the buffer gets free, until at least one slot. If the buffer is free, then only it can. So it is waiting. So if this condition is false, it means that there is some empty space in the buffer. So what it will do? So it will be storing. So I'm making. So the producer is keeping track of this one using a variable called as in. Always in points to the next free slot. In points to the next free slot. So I'm representing this one buffer.in is equals to next produced item. Then after assume that this is in is pointing to here, so it is empty slot. Now next item produced is occupied here. Now I need to increment the buffer value to in, because in always should point to the next free slot in the buffer. Then after that, because we produced item, then automatically I need to increase the count variable also. Earlier they are assumed that there are 9 items in the buffer. Now because I produced this one, the number of items will reach to 10. So that is the code here, counter plus plus. Clear? In a similar manner, we are going for consumer process also. This is a code for consumer process. So here also there is a check. So a consumer cannot consume from the empty buffer. For example, if this is a buffer, so if there are no items, if the buffer is empty, then the consumer cannot consume anything. So to check that whether the buffer is empty, or at least if it is empty, or there are some elements in the buffer, here is the condition. So as we mentioned that the counter will always specify the number of items in the buffer. So if the counter is equals to 0 means what does it mean? There are no items in the buffer, it is empty. So what is this one? The consumer cannot consume. So it has to wait for some time until producer produces the next item. Clear? So if this condition is false, then what does it mean? That there are some items in the buffer. So what it has to do? It has to consume that item. So just like in, the consumer also maintains a variable called as out. So out always points to the next item that needs to be consumed. So here we are making this one. So buffer dot out, whatever the element that is pointed by out pointer, that element is moved to the next consumed variable, that is a variable of the consumer. So that element is moved to the next consumed. So as it has consumed, so what is it has to do? It has to point to the next item that needs to be consumed for the next time. So what we are doing, we are incrementing the out value. Out is equals to out plus 1 percentile by buffer size. Clear, right? So after that, because we consumed, I'll assume that there are 8 items in the buffer before consuming, and after consuming, as there are earlier there are 8 items. Now consumer has consumed 1 item, so the number of items that remain in the buffer will become 7. So that is done by counter minus minus. Clear, right? So this is the code for your consumer process. But because these two codes, either the producer or the consumer, they are written in high level language, so this counter plus plus or counter minus minus, it appears to us as a single statement. But actually, this counter plus plus or counter minus minus, this statement, these are high level languages. So these languages are, when translated to the machine level language, these are not a single statement. These will come into 3 different statements. Let's see what are those statements. For example, so if it is converted at counter plus plus statement, so if it is converted into the machine level language, actual execution of the system, so here it is represented, the single counter plus plus statement is achieved using these 3 assembly level language statements. So assume that I am having the register, so the counter value, whatever the counter value it is there, the present counter value is moved to some register R1. Okay, then the updations, the addition is performed on the register 1. So now register 1 is the update, the increment operator is done. So the increment operator is there, register 1 plus 1. Then after that, once the register 1 is updated, it is again updated back to the variable counter. So this single statement in high level language is equals to, that single statement counter plus plus is equals to 3 machine level statements in the machine level code. Clear, right? In a similar way, for counter minus minus also, the code is like this. Assume that it cannot always, we cannot say that always the register 1 is occupied. So the system might have allocated the register to when this process is executing, it might have taken some register to. Clear, right? So this is the scenario. There is no rule that always the counter should be going to the register 1 only. It depends on the system allocation. Clear, right? So now I replace this counter plus plus with 3 statements and counter minus minus also with these 3 statements. Now assume that these two processes, now producer and consumer, they are running concurrently. So concurrently means they are running in an interleaved manner. Okay, so now let's see some scenario. So here is a scenario. So in the scenario, assume that before the consumer or the producer start execution, let's assume that the value of counter is equals to 5. Okay, this is the initial value of count. This, what does it mean? That this indicates that there are 5 items in the buffer. Now in this scenario, the producer process start execute. Assume that the size of the buffer is 10. So the producer start execution. So after executing, what is thing? It has produced some item. Now what should be the counter value? So after execution, if I follow this code sequentially, so after producing, the counter value is incremented by the producer. That is counter plus plus is executed. So the counter value is 6. Okay. So this is a counter value. Now assume that after producer completed its execution, then consumer process also ran one instance of it. So what is the value of what is the counter value? Now after producer execution, the counter value is 6. Now the consumer also ran, and after completing this one, what is the consumer will do? It will decrement the value of counter by 1. So what is the value of counter? It is 6. Now After running this consumer, again the counter value becomes 5. So if this is a sequence, so earlier the counter value is 5, so the producer ran for one time, so the counter became 6. After that the consumer process also ran one time, so again the counter value becomes 5. So this is, if the both the process run, this is the actual scenario. So earlier there was 5, producer ran one, producer process ran one time, so it became 6. After that consumer also ran, then again the counter became 5. So this is the correct value for me. But if I'll show that there is a possibility that I can achieve the value of 5 or 4, 5 or 6. So these 4 or 6 are inconsistent values. These 4 and 6 are inconsistent values, but there is a chance that the system can generate any of these 3 values, 4, 5, 6. So how I can generate this 4 value, how I can generate 6 value. So this, if proper care is not taken, there is a chance that we may get 4, 6 along with 5. So here is a scenario where it can show how the counter value will become 6. So assume that at time slot T0, the producer started its execution and it has executed the statement. What is the statement in the producer? We are having the counter plus plus is replaced with 3 different statements. Now what is the first statement? So the counter value is moved to the register 1. So what is the value of this counter is having? So 5. Initial value of counter is 5. So after the execution of this statement, the register R1 will get 5. Clear? Now at time T1, the same producer is running. What is the second statement? The register 1 is updated. It is incremented by 1. So this statement will execute. So the register 1 will get the value of 6. So meanwhile, due to some IO event or some event, due to the this time slot or something, where assume that we are going for a round robin algorithm. As the time slot completed, the dispatcher has removed this process producer from the running state to the ready state, and it has allocated the CPU to the consumer state. So at that time T2, the consumer process start executing. So assume that, so the consumer, what is the first statement for counter minus minus? So here is the register 2. So the counter value is moved to the register 2. What is the value of counter? So after this statement, earlier it should be the 6, but the producer has executed only 2 statements. So the counter value is still 5. So what is here? The register R2 will get the value of 5 at time T2. After that, the consumer is still running. So at time T3, so what is this one? It is performing the decrement operator. So this register R2 will get R. Now after this one, the consumer process also got, due to some event or something, the consumer process also got went to a waiting state. So meanwhile, the producer might have completed that event. Now the CPU is allocated to the producer statement. So at time T4, the producer, what is the left out? We know that the execution will start from the statement where it left. So it has already completed 2 statements. So it will start the execution from the start third statement. What is the third statement we are having? We are moving the value of register 1 to the counter. So in this process, what is the value of register 1? As per our this thing, it is 6 is there. So the value of 6 is passed to the counter variable. Later on, so the producer has completed its execution. So it has completed. Now the consumer process, still one more statement is there. So now the CPU is allocated to the consumer. So what is the statement? The last statement it is left out. It is counter is equals to register 2. So what is the value of this register 2? It is 4. So now the counter will get 4, which is a wrong one, because earlier there was 5. We have added 1 to the 5 and removed 1 from the resultant. So the correct answer should be 5, but we got 4. If, how do I get 6? if these two statements are interleaved. For example, at time t4, this statement has run, and at time t5, this statement has run, then it will result in the counter value as 6. So here is a possibility. So as per independently, the logic for producer and consumer is correct, but when they are run concurrently, there is a possibility, like we may end up in wrong results, that is 4 or 6. So this problem has arrived because of race condition. What is this race condition? It is a situation where several processes access and manipulate the same data concurrently, and the outcome of the execution depends on some particular. Because if this is the order, just now from T0 to T5, the counter value is getting 4, or it may get 6 also. So because of this orderly execution, and many processes are trying to manipulate the same variable at the same time, that is same data concurrently, then that condition is called as race condition, and the outcome is dependent purely on the order, or along with the in what order the instructions are executed. So that condition is called as race condition. So when when we are executing concurrently this cooperating process, there will be a race condition, and if proper care is not taken, will end up in inconsistent data. So we need to minimize, it's not minimize, we need to avoid this inconsistent data. So to avoid that inconsistent data, we need to synchronize the process. So what is our definition? We defined that the ensuring the data consistency of the cooperating process by having a proper order is called as process synchronization. So I need to ensure that always when cooperating processes are running, the data consistency should be maintained. So that ensuring is called as this process synchronization. Clear, right? So now we'll define what is critical section problem. So the critical section problem, so before defining this one, first we'll define what is the critical section problem. So the critical section problem is to design a protocol that the process can cooperate each other by ensuring only one process, if any, will be in critical section. So here, when the cooperating process, when more than one cooperating process are running in the system, so what I need to do? I need to design a protocol. I need to create a protocol such that this protocol always ensure that only one process will be in its critical section. So I am defining one more term called as critical section. So what do you mean by critical section? Critical section, so every process, if I divide them, I can divide into two segments called as critical section and remainder section. It is that section where changing of common variables, that is shared variables. Common variables means here for producer and consumer, the common variable is counter. So where there is a change of common variable or updating a table, the table is being maintained or being used by n number of process, or writing a file, because we know that a file is also used by more processors and so on. So it is that segment of code where we are updating the common resources, particularly the data resources like variables, tables, or file, and so on. So that section is called as critical section of that process. And remainder section is that section which do not contain this critical. Apart from critical section, the remaining code is called as remainder section. Clear, right? So that is the thing. And so how we can ensure this pattern? So if you observe the figure here, assume that this is some process P, a general any process P. A typical process P always will have two sections, namely a critical section and the remainder section. So what is this protocol will do? I need to create a protocol such that, what is critical section? I need to create a solution such that a protocol, it will ensure that if there is some process, assume that we are having two processes P0 and P1. Assume that these two are the two processes, cooperating process, just like producer and consumer. These two are executing. So if this process P0 is in its critical section, then P1 should never enter into the critical section. So both process will be having its own critical sections. If P0 is in its critical section, then P1 should not enter into its critical section. So that ensuring is called as that protocol is called as critical section problem solution. So what is the thing? How do I ensure this one? So I'll create two more sections called as entry section and exit section for all the processes. Wherever there is a critical section into this one, when a process P0 or P1 and so on, before entering into the critical section, I'll have an entry section. What is this entry section will do? These two sections will decide that whether this process should enter into the critical section or not. It will make sure that it will check whether any other process is in its critical section. If so, it do not permit the other process to enter into its critical section. If there is no process, then the process P1 can enter into the critical section, and after doing this, after updating this common variable, then it has to exit. While exiting, when it is entering into the remainder section, it should allow the other process to enter into its respective critical section. So that is the need for entry section and exit. So the protocol will say that all critical sections of the processes, their respective critical section should be guarded by two sections, namely entry and exit section. So this is a general structure of any critical section problem solution. So we need to create that entry section and exit section. So now, what are the requirements of this critical section? So this problem, whatever the protocol you design, that solution should have some three characteristics. So if you are creating new solution for this critical section problem, then it has to minimum it should have three characteristics. If the design solution is not maintaining these three characteristics, then that solution is not recommended, or the solution cannot ensure you the proper exit process synchronization. So let me see that what are the three requirements of the any solution critical section problem should have. So any solution you design or you create should have at least these three minimum requirements for this critical section problem. So what are those? First and foremost requirement is that it should ensure mutual exclusion. So what does this mutual exclusion characteristic will say? That if a process Pi is executing in its critical section, then no other process can be executing in their critical sections. So for example, process Pi is already in its critical section, Pi. Okay. Now Pj is trying to enter into its own critical section. So, but there should be some communication to the Pj should be aware of that through some means already Pi is in its critical section. So it should not enter. So that ensuring is called as allowing only one process in its critical section and not allowing more than one process in their respective critical sections is termed as mutual exclusion, and this is required. So this is the first and foremost requirement. If this requirement is not satisfied, then we cannot trust that critical section problem solution. So that is it. And the second property is that progress. So what is this progress characteristic? Will say that if no process is executing, assume that there is Pi is in its critical is in remainder section, and Pj also in remainder section. Now Pj wants to enter into its critical section, but always whenever if there is no other process in a critical, the Pi is not in critical section, then the Pj, nothing should stop Pj to enter into the critical section if there are no other process in the critical sections. And if so, for example, assume that we are having Pi, Pj and Pr. Assume that Pr is in its remainder section, and Pi also, both Pi and Pj wants to enter into the critical section, then the decision whether Pi or Pj who has to enter into the critical, who has to given the chance to enter into the respective critical section is decided by only PI and PJ. There is no role of PR because the process is already in its reminder section. So there is no way, it is no way concerned. So when only those processes that are not, only those processes that are trying to enter into the critical section, only those should decide who has to enter into the critical section, because already PR is in, it don't want to enter into the critical section, it is running in reminder section, there is no need for it. So the decision should be taken by only PI and PJ. Unnecessarily we should not disturb the PR. Clear, right? So that property is called as progress. And third property is that bounded waiting time. For example, the protocol assume that the PI, PJ and PR are trying to enter into the critical section. As per protocol, PI got the, as per the protocol, PI, the protocol has allowed PI. Okay. Now PI completed its execution. After its execution, PJ also enter into the critical section and PR. All this PI, PJ, PR are waiting. So PI got the chance, it has entered into the critical section, completed its portion, and it is in reminder section. So meanwhile, when the PI is in reminder section, the protocol allotted PJ, the critical section, the PJ also in a critical section. Now, meanwhile, again PI wants to enter into its critical section, so again it came back. Okay. So when PJ completed its critical section critical section, then again the protocol is giving favor to PI. But since past few minutes onwards or past time, the PR is waiting, but the protocol has allotted to PI. Like this, again PI completed, again PJ. So the critical section is being allotted only to PI and PJ. Then there the PR, the process PR is waiting much time. So that thing should not happen. So whenever there exists, so what is this characteristic will say that there exists a bound or limit on the number of times that other processes are allowed to enter. So PI entered first time, again PJ entered, again PI entered, again PJ entered, it is going. So I need to have some bound, because PR is also waiting, the PR is getting starved. Only these two processes are getting the chance to enter into the critical section. And the protocol is designed such a way that it is favoring only these two. So it is not favoring this PR. So I should not have any flaw in my protocol, that I need to have some limit on the number of times the process PI entered. For example, it has entered 2 times. Then I'll keep this maximum bound as 2. And when PI wants to enter the 3rd time, then I do not allow this one, because already it has used 2 times. Now I'll give the chance to the PR. So that thing also be waiting. I need to have a bounded waiting. All the process should have a certain time. They need, if a process wants to enter into critical section, there is a certain time there. The time is limited, that bounded waiting. After that, without any irrespective of this one, we need to allow the process which is already waiting from long time to enter into the critical section. We need to allow that process to enter into the critical section. Clear, right? So these 3 properties are foremost important. All these 3 properties should be maintained. Then only we can call that solution as a good solution for the critical section problem. Clear? Now, how to create this critical section? What are the different approaches for the critical section problem? So I can have 2 approaches. One is hardware approach, and the second thing is software approach. So in the hardware approach, what are the examples are? I can disable the interrupts. I can disable the interrupts by when a process is in a critical section. By simply disabling the interrupts, the process cannot get interrupted. So until it completes its critical section, then only it will come out of that one. Or using the special instructions like test and set, I can achieve the solution for the critical section problem. Okay. And the other thing, software approaches, I can create some of the software things like lock. It is called as mutual exclusion log, mutex logs. In short, it is called as mutex logs. The mutex stands for mutual exclusion logs. So these logs will ensure the mutual exclusion. That's why these are called mutex logs. Or I can create one more data structure called as semaphores, or I can have a utility called monitor. Using any of these things, I can achieve this critical. I can create the solutions for this critical sectional problem. Clear? So these are the approaches. In the next class, we'll discuss with hardware approach, then followed by software approach. So coming to the summary of the today's session, we have discussed what do you mean by process synchronization, and also we have seen the need for process synchronization when we are having concurrent execution. Okay. Also, we discussed what do you mean by race condition and the critical section problem and the approaches for the critical sectional problem. Clear? So we also seen the what are the three requirements a solution for critical section problem should have, and this thing. So this is the thing. So all the material and this that are being used in this thing are taken from this textbook. Abraham Silberskach, Peter Galvin, and Greg Hackney. The textbook is Operating System Concepts by Wiley Edition. Okay. So this is the feedback thing. So you can give what is the your valuable feedback for this thing. Thank you so much.